This is Porterville College, Physics 102B, Chapter 15, Homework Solutions, Part 2, starting with number 53. What is the electric field a distance 1 millimeter from an electron? We use this equation. Electric field is our constant K times the absolute value of the charge, divided by distance squared. So there's K, 8.988 times 10 to the 9th. The charge on an electron, just using the absolute value, so positive, divided by 10 to the negative 3 meters squared. So we get 0.0014 newtons per coulomb. The question didn't explicitly ask this, but if we want to know the direction, remember how to draw your field lines. The field lines go in towards a negative charge, and so this shows the direction. No matter where you are around the electron, the electric field is pointing towards that electron. Number 57, for the dipole given in this picture that I've drawn, compute the electric field at, we're just doing part A here, so on the x-axis at negative 15 centimeters. So here's our negative charge, here's our positive charge. They're both negative 2.5 nanocoulombs, and we're computing the electric field right here. So we need to figure out both the magnitude of the electric field given by Q1 and Q2, and also the directions. So let's take the electric field from 1. It's K times the charge of 1 divided by the distance squared. So the charge of 1 is 2.5 times 10 to the negative 9 coulombs, divided by, we're looking at a distance here of 5 centimeters squared. So the electric field from charge 1 is 8,988 newtons per coulomb. Now, I put a positive sign there because we also have to evaluate what is the direction. So just as in the previous problem number 53, the direction of an electric field line is going towards the negative charge. Remember, when you're contemplating direction of an electric field, you should ask yourself, which direction would a hypothetical test charge be pulled? A positive test charge, and it would be pulled to the right in the positive direction. So that's why E1 I'm putting as positive. E2, the electric field from charge 2. First thing you can see in the blue, I've put here a negative sign, and that's because charge 2 is positive. So a positive test charge to its left would be pushed in the negative direction. So whatever we get, it's going to be negative. Plug in the values, K times the absolute value of the charge divided by distance squared. Now the distance is 25 centimeters, or 0.25 meters squared, and we get 360 newtons per coulomb negative, and that is the contribution from charge 2. So the entire electric field is the vector sum of E1 plus E2. That's 8988 newtons per coulomb to the right, and 360 newtons per coulomb to the left, so I'm subtracting those, and I get a net electric field of 8600 newtons per coulomb, and it's positive, meaning pointing to the right. Number 61. A charged plane has a uniform surface charge density of negative 1.5 times 10 to the negative 7 coulombs per meter squared. How many electrons will be on the surface in a square that's 1 millimeter on a side? This is really just playing with the definition of density, or charge density. Charge density, which is sigma, is charge over area. We're asked to find something about the charge, so charge equals sigma times area. So we multiply sigma times the area, 1 square millimeter. We need this in meters, so we do our unit conversion, 10 to the negative 3 meters divided by a millimeter. We need to square that to get square meters. And we're left with a charge of negative 1.5 times 10 to the negative 13 coulombs. Now we need to know how many electrons is that. So I treat this mathematically like a unit conversion. I take the given information, here's the charge, and I multiply by 1 electron, which is equivalent to, so I put it over negative 1.602 times 10 to the negative 19 coulombs. The units of coulombs go away, and we're left with the number of electrons, approximately 940,000. Number 63. A pair of charged parallel planes. The net electric field, we learned in class, from a pair of oppositely charged planes is sigma over epsilon naught. So sigma becomes the electric field, the net electric field times epsilon naught. So 10,000 newtons per coulomb times epsilon naught, which is the permittivity of free space, 8.85 times 10 to the negative 12. So we get that sigma, the charge density on each plane, is 8.85 times 10 to the negative 8 coulombs per meter squared. Number 65. Hydrogen atom with an electron and a proton. There's the distance between them, the orbital radius. What is the electric field acting on the electron? So we're going to be looking for the electric field that is produced by the proton and find the force acting on the electron. So the electric field at that certain orbital distance that's produced by the proton is k times the charge in the proton divided by r squared. So there's our k times charge of a proton, that's the elementary charge, divided by the distance squared. And you should get for part A 5.15 times 10 to the 11th newtons per coulomb. Question B asks, what is the force then on the electron? Force is equal to the charge of the electron times that electric field. So we get about 8.24 times 10 to the negative 8 newtons. By the way, part B, you can see what I've written here in the blue. Part B could have been solved just by using Coulomb's law. Coulomb's law, we could have just done k times the charge of a proton times the charge of electron divided by the distance squared. And it would have given us the answer we got in part B. We just, in doing part A, then B, just took that through two different steps. Number 71. A small bit of photocopier toner. There's its mass. It carries a net charge of 2 times E. There's its acceleration. What is the magnitude of the electric field that causes that acceleration? So we have an electric field going to be equivalent to the force on the particle divided by the charge of the particle. Newton's second law says the force on the particle is ma, mass times acceleration. We're given that the charge of the particle is 2e, so the electric field is then ma divided by 2e. Plug in those values, and you should get 5,460 newtons per coulomb. Number 73 is very similar to 71. Acceleration given of the electron. We're dealing with the direction also. Find the electric field responsible for that acceleration. So we're going to find magnitude and direction. Just like in 71, electric field is force on the particle, in this case the electron, divided by its charge. Force is mass times acceleration. We're dividing by the elementary charge. You have mass of an electron, 9.11 times 10 to the negative 31 kilograms, times the acceleration, divided by the elementary charge of 1.602 times 10 to the negative 19 coulombs, and you get an answer of 185 newtons per coulomb. Now let's talk about the direction of the electric field. It says that the electron is being accelerated at an angle of 30 degrees above the x-axis. So the direction my pen is pointing, that looks about 30 degrees above the x-axis. Remember that electric field lines point in the direction that a positive charge would be forced. The electron is a negative charge, it goes in the opposite direction. So a positive charge would be forced this way, the way my finger is pointing. So the opposite direction of 30 degrees above the positive x-axis, you could say, is 30 degrees below the negative axis, or as I've done here, 30 degrees just add 180, so it's in a direction of 210 degrees. The final question, number 81, pulls in some kinematics that we learned back in Chapter 2 of first semester. We have an initial speed, a displacement, and a final speed of 0. We're going to solve 81 similar to how we did 71 and 73. We're going to use electric field is force divided by charge, which then becomes mass times acceleration divided by charge. We know the mass of, what are we looking at, of an electron. We know the charge of an electron, but we're missing the acceleration. So let's come up here. We need to use a kinematic equation, and you can go back to Chapter 2 to review those kinematic equations. But acceleration is velocity squared, final, minus initial velocity squared divided by 2 times distance. Final v squared is 0, that just goes away. So we're left with negative initial velocity squared divided by 2 times distance. Remember, we need meters, so don't just plug in 9.2. It's going to be 0.092 meters. And we're left with an acceleration of 2.397 times 10 to the 13th meters per second squared. Now we can take that acceleration, plug it into this equation, mass times acceleration divided by charge, and we get 136 newtons per coulomb. Question B asks, what is the direction of the electric field relative to the electron's original motion? So it helps to draw these different vectors here. The original motion, I have it in my picture going to the right. The electron was decelerated, it was slowed down, meaning the direction of the electric force, it was accelerated backwards. So the direction of the force is backwards or to the left. So we contemplate an electron that has been forced to the left. And we remember that electric field lines go in the direction that a positive charge would be forced. A negative charge goes in the opposite direction. So if a negative charge was forced to the left, that means a positive charge would be forced to the right. And so we have the electric field line going to the right. But to answer the question properly, because the question, the way it's asked, doesn't specify left or right or up or down, we can say the electric field goes in the direction of the electron's original direction of motion.